EVM proved in 10 seconds. The race to real-time proving. We'll have Francesco from Consensys and MetaMask as our moderator, and panelists Arthur Remy from Linea, Stephen Duan from ZKM, Michael from Brevis, and Haichen Shen from Scroll.
Michael, you wanna start first?
Oh yeah, I can start. Hi everyone. Thanks again for coming to our event today. We're kind of the host here today, and I'm Michael from Brevis. I'm the co-founder and CEO of Brevis, and we built, as you know, the ZK verifiable computing platform, and two main products. One is our Pico ZK VM, and also the coprocessor. We recently also announced the prover network is gonna have like a decentralized proving and high availability and everything. So happy to be on the panel here today.
Hello everyone, this is Devcon from ZKM, and ZKM focused on building MIPS-based ZK virtual machine, and the MIPS are compared to the what we use. I say like RISC-V. MIPS is more mature, more established. I think a lot of controller sensors software are built on the MIPS. And we also more focus on the dev-friendly toolings. We support multiple languages like Golang, Rust, C++. Yeah, so basically that's the game.
Hey everybody, so Arthur from Linea. We are a ZK rollup technology, one of the team that are developing ourselves the prover since 6 years. So very excited to talk about that.
Hi everyone, I'm Haichen from Scroll. I'm co-founder and CTO at Scroll.
Nice. I'm Francesco, leading developer relations at Consensys, and I'm excited to host this panel, right? So Mo, thanks so much again for hosting us here. And I really like the fact that it's actually a conference specific for ZK, right? And so in context for the other panels, so this is all about kind of like speed. So EVM proved in 10 seconds. So let's just start a bit, and this is a question for all. So why kind of like this sub 10 second proving is so important for the entire kind of like EVM roadmap?
So yeah, I think like the importance is mostly because the EVM block is 12 seconds. So if you can prove within 10 seconds, then you can basically almost like achieve real-time finalization for the Ethereum.
For ZK VM, for some of the new audiences, just kind of let me repeat this here. Today, if you look at the consensus protocols, right? So like you got a bunch of nodes that are trying to achieve consensus, means that they want to agree with each other on certain outcome of computations. And today the consensus is done in a replicated computation way. So like basically you want to essentially replicate it across the entire network to say, okay, now we all agree like swap A to B is a result to C. However, the challenge here is that because of Ethereum layer 1 specifically has like a huge amount of nodes, it's super decentralized with I think 800k to a million nodes. So what this means is that, even if you're just doing some very simple computation on this network, it needs to be replicated about 1 million times. And, that immediately gives you like a kind of a million times inflation in terms of the computation cost. And on top of that, you have a communication cost across the node. And this is why fundamentally, blockchain execution in layer 1 is kind of expensive. A way to solve this is to change the computation paradigm from replicated computing to verifiable computing. That you have one node that does all the computation that you want, and then all the other nodes will just like simply verify a ZK proof of the computation. And then once the proof is verified, then everyone kind of can achieve consensus. And the importance of 10 seconds, of course, is that, right now the blocks are, produced every 12 seconds, produced and propagated every 12 seconds. And, we want to essentially press the, if you have like one node that is proving Ethereum, we want it to be able to prove that within 10 seconds. And this is actually a benchmark that is set by Ethereum Foundation, by Sophia Gold. And, to actually kind of achieve this benchmark with this 2-second additional room, we can actually propagate the proof through the entire network.
I think the sub 10 seconds proving, maybe we say real-time proving can provide like low gas fee for the end user and higher capital efficiency for the holders. So as Misha has mentioned, that like we can shift the on-chain computation to off-chain and verify the proof. Then you can save a lot of gas. And on the other hand, for the capital efficiency, like for example, when we launch the ZKM, actually we are trying to decrease the final time of Metis optimistic rollup to like from same days to like 1 hour or less. So basically, it's also suitable for a lot of other ecosystems layer 2, like the Bitcoin layer 2. Yeah, so basically that's a point.
So as Over mentioned, like it helps scale the L1, but I also want to stress that it helps L2s actually. So like the very basic version is that if you prove faster, you can finalize faster. But you also have this thing called the native rollup that is on the Ethereum roadmap, where like my mental model for it is that we are just trying to embed like a ZK rollup within the Ethereum layer. And so the way it works is basically instead of like having each rollup to develop their own proof system and also like having to verify it on chain through the smart contracts, you have this execute precompile that lets you do that more like on the consensus layer and in a standardized way across all the rollups. And this brings a lot of nice properties. Like the first one is the security, because if it happens on the consensus layer, you get the upgradability directly on the consensus layer, and this means you can get rid basically of the security conceals, because like the consensus layer will just take care of the upgradability. You don't need anymore the smart contracts, so you don't have the smart contracts risk, the risk of bugs, and also you get much faster finality and lower cost.
I think this is a good context. So one kind of like follow-up question, obviously, is the 10-second kind of milestones is pushing boundaries, right? And maybe like a quick first question, and this, I will not be spicy today. I will try to not be spicy today. Full scroll and Linea, right? So you're both obviously pushing around EVM equivalencies. What are kind of the trade-off that we need to kind of like think about it? Because obviously there will be some trade-off around architecture side, and I would love to know like also the direction that you both taking here.
Yeah, I think like the trade-off mainly is that Ethereum itself, like the EVM especially, is not optimized for the ZK circuits. So that's why like if you want to achieve 100% compatibility, we need to, so the circuit must be more complicated. And also, for example, there's a lot of precompiles that's like a very complicated to supporting the circuit, which it's very expensive to be proved inside the circuit. So you need to write a dedicated circuits. It's almost like an ASIC inside the ZK circuit that can optimize the performance into a more practical level that to prove that. I think like in the beginning, like when we first like building the first iteration of the ZK EVM, is like it does like the making the circuit very large, and then also the proving cost is relatively high. But with like more and more advancement of the ZK technology and the new protocols coming up, like small fields fry, there's all of those things like that. Now like it's driving down the cost by a lot. So as a previous I'm gonna scroll, like the transaction cost is mostly it's dominated by the ZK proving. So and now like it's with the ZK VM and then it's better ZK technology. Now the proving cost is driving down by a lot. If you build an ideal EVM, like it's like you don't build an EVM, then you build like other VM. So you can probably like still be more efficient by using some ZK friendly hash functions, not using cache hash. So that probably we're reducing a lot of the cost. But I think, at the moment, I think it's no longer a bottleneck for the ZK VM to be achieving the real time proving. Because like the cost for proving a single transaction now it's like 0.40 like some cents, like that kind of like it's very cheap. So I think like it's like good, like so now actually Ethereum just like I think we can almost like achieve to proving the Ethereum real time. It's only the things like I think if you really want to put into production, it's like there's some extreme cases whether like if people are trying to just DOS attack the ZK VM, then they can probably call a lot of those heavyweight functions in the ZK VM so that making the proving time becomes longer.
But do we need to sacrifice something specifically or no?
I don't think we need to sacrifice. Yeah.
On the Linea side, like we have a different approach as others. Like we really believe on direct proving of the EVM execution rather than having, as mentioned, like an intermediary virtual machine that then like run the EVM. And we think that at the end of the day, it will be more efficient. One way it materialized today is that just without any hardware improvement and only like CPU, we are already at like a very good stage, and we plan to achieve real-time proving early next year. And so we think that will be much more efficient. Obviously, like the big trade-off is that it's harder to do, it's harder to develop, but we think once you get there, that's really good efficiencies. And instead of having to run very expensive machine with multiple GPUs cluster or one GPU, you can just run it in almost commodity hardware, which is a nice property while still having like the benefit of the speed.
Nice. Yeah, I love the answer. Oh, Michael, you want to chime in?
Yeah, so just on the kind of a trade-off question, right? So like we're trying to kind of prove Ethereum execution in real time. And, if you look at the entire performance profiling today, a lot of the kind of cycles on the ZK VM proving of the EVM execution is actually spent in the data manipulation part of this. So like, right now, Ethereum, if you look at the entire kind of Ethereum block construct, is that it's organized as a kind of a Merkle-Patrician tree. And, all the hash functions are like Kachak hash functions. And, I think we are at this point that, we have proved that a ZK and the verifiable computing, is actually possible to be used as kind of a new way to run consensus. Now the next step is to look at the consensus itself, look at the VM stack itself to see if we can actually modify the EVM a little bit to actually make the EVM itself like more ZK friendly as well. Right, so like you can imagine, you can use there are a lot of discussions in the Ethereum Foundation about using universal binary tree and a new kind of a hash function called a Poseidon hash to kind of rewrite the entire state construct of Ethereum so it can be extremely kind of ZK friendly, and that gives us another order of magnitude performance benefit immediately. So that's something that, I think, we as a community need to start to think about because, ZK has proven that it is capable. Now, like the VM need to kind of go the other direction to meet us in the middle as well.
Actually, like I have a different view from this. Is like, so I used to believe that we should modify the EVM. For example, like when we initially designed the Scroll protocol, we have like an internal debate whether we should use actually like we're using a different tree structure. We're not using the Merkle-Patrician tree because we're using Poseidon, so to be more efficient to building that, like as a trade-off. But like after now, like the ZK has advanced. Now, like if you're using the ZK VM and using the small field, I realize like if you're now proving the Poseidon inside the ZK VM with the small binary field, or like even a small finite field, then actually that's like using the Poseidon hash function is more expensive than using the regular Kachak hash function. That's like something like I realized afterwards is that, okay, the ZK can keep like improving. Now, if you customize your protocol to a like certain generation of the ZK technology, then you may be like locked into this ZK technology. And then if the ZK keeps improving, then you maybe like found that it's suboptimal. And also there you need to balance between the execution speed in the CPU versus executing like proving costs in the ZK VM. So like you need to balance. If you're using something like the more friendly to the ZK, then the throughput, like the execution speed on the CPU becomes slower. The CPU is better at manipulating the binaries, not the prime fields. So that's why like there's like a trade-off between these two. So for the long term, I still feel like we should optimize like the protocol against the CPU execution speed, and then the ZK is kind of catching up and it keep like iterating and then improving.
I like when there's disagreement in panels. Please do more. And on the ZKM side, how you guys kind of like approach real-time proving?
Real-time proving, actually, it's first we consider the emulation, then the proving. For the emulation, actually, we are working on it with, especially in the last few weeks. We spent a lot of effort on that. And we found that Bottleneck steer the emulation because MIPS is a bit different from the RISC-V because we have more, we have about 64 instructions. I think it's much more than the RISC-V instruction says right now. So that means our trace table is more And we also have some complex instructions like the multiply and add, multiply and sub. So that means our table is more wider. So actually it can make the trace size smaller. Basically, it can minimize the proving area. But for the emulation, you have to operate more variables for each instructions. Okay, so that's why we our emulation speed is much slower than the other ZKVMs. Okay, that's the first. For the second one, for the proof side, we think we spend a lot of time on the CPU and the GPU memory management, like the pin page, like the pre-allocation on the device side, the device memory. But I think that's already very fast right now. To be honest, we already set up some real-time proving for some other our use case, our users, but not right now. A lot of ready for the Ethereum Foundation, but it's proof. But I think we can do that maybe in the next few weeks. Yeah.
Yeah, I did some research around ZKVM. I remember like also a lot of feedbacks around the friendly developer tooling. So that's really positive. This is for you, Michael. But since yesterday, I know you're a fan of State Channel, if you're night. But there is another thing that you mentioned a couple of times around ZK Processor, right? So how kind of like you see, like maybe give a context also what are ZK Processor in a nutshell, but how this is kind of like affecting verifiability and obviously like the goal to get to this 10-second milestone.
I think if there's anything that I want to kind of be a takeaway for today's panel is that we are at the point for ZKVM and to prove the Ethereum block that is so that the entire Ethereum scalability today is now a pure money problem. Okay, so that's something that we never achieved before, and we saw it was not possible. So we can maintain the same level of decentralization and just keep throwing money and kind of build larger and larger kind of server stacks with more GPUs, and we get much better and 10 times, 100 times scalability today. We can do it today. We're still going to improve the efficiency side of this, but for the ZKVM itself, it is already at this point that the proving is highly parallel, and you can break very, very complex Ethereum blocks into small pieces and prove these smaller pieces concurrently, and then kind of aggregate them into a single proof with almost no kind of overhead. So we have basically achieved the holy grail of kind of Ethereum scalability, I would say. But it is not enough. Because, for many applications that want to run on blockchain, you want it to be running faster than what a single server can provide, right? So in the end of the day, if you look at every single blockchain, they're running consensus protocols, they can run faster than a single server. So this is where you actually need to also think about how you scale application level computing with something additional. So this is where we introduce the concept of application level coprocessors that allows you to use the ZKVM as a glue and plug in a different kind of application level specialized circuit and specialized system, so you can continuously just throw all these kind of heavy computation off chain that is entirely not running in the consensus system, being a kind of a separate environment, and generate a proof there to kind of bridge the proof then back to the smart contract level to verify the computation itself is done correctly in an off-chain environment. So with this kind of new way of doing verifiable computing, you essentially have the capability to tap into infinite amount of computation resources, because you can essentially run computation in parallel, but in a verifiable way with the same level of security that Ethereum Layer 1 provides. That's where we really need this kind of application level coprocessors to deal with use cases such as you want to build a user profile, you want to customize user experience based on their historical on-chain behavior, you want to customize your lending protocols, borrowing and lending fees and everything based on market conditions. This is where you actually need to have this kind of application level coprocessors that is not just a general VM, but specialized in generating proof for these kind of historical data, and then, plug that into your core business logic that is running in the VM. And, things like ZKTOS is also another great example. We work with, some great team like Brevis to kind of, integrate their ZKTOS as a coprocessor for our ZK VM. So you can essentially pull in a bunch of Web2 data that you have, like if you traded a lot on Coinbase, or, what's your spending level on your PayPal account, and pull all this information in and then do some computation in our ZK VM, and to get it verified on-chain to build kind of a modern generation of credit systems, on-chain as well. So yeah, all these kind of things are, only possible if you have this kind of an application level coprocessor and the modular architecture that we build.
We spoke about kind of 4 main category, and I wrote it down, right? So on the first one, obviously, we have one category around circuit compilation. The second one was proving algos, hardware limitation, and data I/O. I would like to understand, out of these 4 categories, what do you see are the kind of like bottleneck, the things that we need to kind of like, solve right now, and they are most priority for us? Quick answer only, and then please prepare some question, guys.
So maybe I will start. We have a bit different approach than more on the Brevis side, where we don't want just to throw big amounts of money to prove things, especially when you want to prove the L2, because you want the transaction for real user to be as cheap as possible. And if you with the current approach, it's still multi-sense. So the way we are doing it is just optimizing as much as possible the algorithms, so the raw efficiency. And as Haichen mentioned previously, with small fields, this is an upgrade that's coming to us in January. Normally, we will from 10 to 100x improve the performance. So that will be massive, real massive, and that's the thing that we are prioritizing at the moment, and we think it will get us there very quickly. And when we are there, adding more compute, more power is the easy part.
I think I will answer this question, but I need to mention our approach how to speed up the emulation. For sure, stop block is the first approach. The first step, and the second one is how to do something like the CPU pipeline to fetch instruction, to execute it, to return, to store the results. So you may use some the CPU pipeline for emulation in the future. Yeah.
I think as kind of my take on this is that we don't exactly have a bottleneck yet. So that's something that is makes me really happy and relaxed about the future of verifiable computing. Because when looking at this whole space, especially for example, Ethereum layer 1 proving, there are just so many low-hanging fruits that we know how to kind of solve them, in the next couple months. And we know that in the next 2 months, we're going to get another 2x performance gain. In the next 3 months, we're going to get another 2x performance gain. We have all these kind of things planned that we know that it just work. And, so that's why I'm super optimistic about the future of using verifiable computing, using ZK to scale Ethereum layer 1 to scale out the applications, because there are just so many low-hanging fruits that we can see, changing the protocol to kind of univariate to multilinear, changing the way you access data on GPU, changing the emulation as Stephen mentioned. So there are just so many things. I'm quite relaxed about the future of verifiable computing.
So any question, guys? Please be spicy. Oh, we have an ear in the back. Do we have a mic? Should I run? Yeah, let's do it.
Okay, no bottlenecks, but I have one concern. It's security. I mean, we improve performance, but there is always trade-off. I mean, think about bits of security and post-quantum. I mean, if we really want to achieve post-quantum, it will fire back into performance again. That's one thing. Another thing, all of those low-hanging fruits improvements that you mentioned, they also can reflect. I mean, they have to be proven that they're really secure if we want to move it to for instance, for Ethereum to L1. That's my first question. And another one, what if, for instance, L1 moves from EVM to RISC-V? I mean, we will have much higher compatibility with RISC-V based witness generation projects. So only those 2 questions. By the way, we are building hardware to accelerate all this kind of, not only accelerate, there is CapEx and OpEx. When you run all this kind of stuff, you need, let's say, bunch of GPUs in server card, and you can replace them with few well-optimized ASIC chips, for instance. Then you have CapEx and OpEx that are much lower, and this really can unlock millions of transactions per second, because now we don't have this problem because we don't have millions of transactions per second.
Yeah, on the security side, I think like that definitely like it's behind, like it's catching up. I think that we should like putting out like more grant, and then like also those auditing, like even going further to the formal verifications like on the circuits, like so that make sure it gets like more secure. I think that for sure is doing that. For example, I think like just a few weeks ago, so I think Shen posted this bounty for finding the bugs inside the fry conjecture, and then they did like find some bugs, and then if they fix that, like it does have some performance hit onto that, like about 20-30%, but it's not like too bad. But I think we should continue doing that to make sure that the security of all of the ZKVM can improve.
This has been solved very, thoroughly in the EF, especially for kind of replacing this, the consensus mechanism with like verifiable computing, because there are several ways, right? So like you mentioned the several things about the security. There's like the code level security, there's like post-quantum security, and there's a protocol security itself. So for post-quantum security, most of the ZKVMs are going to be post-quantum secure, and the performance hit is not going to be that large. And if you look at you really recommend looking at like the kind of a benchmark blog that is posted by EF, and there's like also kind of a number of bits that you need to kind of achieve at least in the near future to be kind of quantum secure and everything. So you can basically use like lattice and stuff like to make it easily achievable, and it's not going to be a huge hit on performance. But like, to be honest, if you really want to kind of roll this out in production, the code are written by humans so far. So like, human can make mistakes, and there can be bugs. So a fundamental kind of a solution for this is to actually have a redundancy in the protocol itself, like to have multiple different ZK VMs, the RISC-V ZK VM or MIPS-based ZK VM to concurrently verify the Ethereum state and generate execution verification trace, and pair that with different kind of clients and stuff to essentially enhance the operational level security of this whole thing. So I think we can achieve that, and there is also a very awesome that is initiative in EF that is like helping every ZK VM team to do formal verification. So at least that can giving you a level of confidence, because fortunately ZKs are building constrained systems, so it's like easier to verify against like a spec. On this there's like great work that is being done by Nethermind and other Veridize and many other kind of teams that is doing this. So, I think we're going to get there. If ZK VMs that were secure today, we would like have already replaced this, the entire Ethereum consensus with ZK VMs. It's just like, that's the thing that we need to do before we can actually make the switch. But I'm confident that that can happen. So you also have a second question about like moving to the kind of a RISC-V based VM instruction set.
Maybe just to finish on the security, I totally agree. Like, practical security is super important. I need to salute like our cryptography team, because like we are already at 128 bits of security. We don't use like the Reed-Solomon conjecture. So I think we are already like in a pretty good place, but totally it's like the job is not finished. And so it's something we need to keep pushing forward.
And we do the formal verification for all our sockets with the Veridize. So yeah, so it's very important. Yeah, and the second part, second point is for ZKVM actually we have a lot of secure assumption, not just the PCS or not just the file or other PCS. It's also need to consider the lookup. I think a lot of ZKVM right now didn't do the end-to-end security audits right now. Yeah, so I think we still need to working or spare effort on that.
Sounds good. So I will quote Arthur and Michael. So the job is not finished, but we are very optimistic.
Yes, we are very optimistic.
So join me for a big round of applause for our panel.